So thank you very much for having me. So I'm Roland Haas. I'm going to give you just a lightning quick introduction to the Einstein Toolkit and how to use it. Word of caution, so this is not the first time we give this talk. We give this once a year, basically, or twice a year, actually. So if you've attended any of the Einstein Toolkit summer schools before, you almost certainly have seen this particular talk. Last time around, it was given by Steve Brandt, and I've shamelessly stolen all of the slides. And the slides are basically handed on from person to person, so we're kind of building on them. So I give it now, Steve gave it before, Frank Loeffler worked on them, Peter Diener. So this is a community effort. You can even find them online somewhere, I think. So in any case, I'll give you first a bit of an introduction. What's the Einstein Toolkit? Both in the sense of what can you do with it, but also a bit of what the philosophy is and what people have done with it. And after that, there's a sort of hands-on session, really small, where we will log into a tutorial server and then just run through a very short simulation with the Einstein Toolkit. So the simulation we will be doing is a single isolated neutron star. This we evolved the TOV solution for fluid ball, and then we just have this thing oscillate a little bit, and we will plot what's the oscillations in there. And that's the same thing that we also have on the Einstein Toolkit tutorial server, just changed a little bit in the sense that I've pre-packaged everything that you need in there. There's a pre-compiled version of the Einstein Toolkit. There's also ready-made data that we will be using. So when we run it, it's set up to run for only a minute. And then afterwards, we're going to use the data that I've produced last night with that same thing, just because it runs too long. It runs about half an hour on the workstation, on the tutorial servers. All right. With that, if you have any questions, if you're in the room, just raise your hand. If you're online, just unmute yourself and speak. And please interrupt me if I'm going too fast, if there's anything off. If one of the hosts can monitor the chat, that would be great, because I think it might put up, but I'm not 100% sure. All right. So with this, so if you look at what the Einstein Toolkit is, the Einstein Toolkit is a collection of scientific software components and tools to simulate and analyze general relativistic astrophysical systems. So it's different in some sense from other things that are of similar nature that you can find out there, not so much because it's freely available, and that is URL, lots of things are, but in the fact that it's from the very beginning designed to be modular. So it's not a unique monolithic set of software that you download that's developed by one group and you just can use it, but it is a set of modules that you can freely change and modify yourself. You can also swap them out. We have in the Einstein Toolkit already 2 different modules that let you do general relativistic hydrodynamics, the GeoHydro code and the Illinois JMHD code. And you can use either one, which one works better for you for a particular problem. Or you can write your own and use everything from the Einstein Toolkit, but swap that out. And that's built into the system. So it's not something that you have to hack in. It's designed that way from the beginning. It was that way. And that's the big difference, I think, to other codes that you can find online by now, that it is designed to be modular and also has had the idea in mind that you will want to share codes with people that you might be competing otherwise scientifically. So it has some things in there that makes this possible, that people that compete for the same scientific results are still able to collaborate in a useful way and share things that they really want to share, say infrastructure. The Einstein Toolkit has been lucky enough to be supported by a number of NSF grants over the years. Currently, there's a grant that funds development of the Einstein Toolkit at 5 institutions in the US. These kind of get money to do that. They're not necessarily the ones that decide what's done in the Einstein Toolkit. That's actually done by the maintainers, which is a different set of groups, has overlap, but it's different. And the maintainers are kind of honorary positions for people that have said that are willing to invest the time to try and steer where the Einstein Toolkit is going, to kind of oversee the development. They are not necessarily the ones who do the development, at least not by design. They are overseers in some sense, trying to balance the interests of different groups. The Einstein Toolkit aims to offer state-of-the-art sets of numerical relativity codes that are all open source. So that typically means that we would take a code that's out there in the wild that was already used for publication and therefore has proven good enough. And then we would incorporate it into the Einstein Toolkit. And then it should be the whole thing, not just a little bit, but you should be able to do the full simulation from the beginning, from initial data for binary black holes, down to the analysis and plotting of your results. Everything should be in there, ideally, and should be well documented. And we are getting there. It's definitely getting there. You can register to be an Einstein Toolkit member, just to show your support. Currently, when I checked this yesterday or so, there were 356 members from 249 sites in 43 countries. It's more now because the website actually automatically updates itself. So it's live. There are upwards of about 400 publications that we have counted so far, about 53 defended theses that were based on the Einstein Toolkit on these components as of June 2022. So the numbers are a bit iffy, but essentially you get emails every once in a while where we say, oh, are you working with the Einstein Toolkit for your thesis? And a certain fraction tells me, yes, I've defended, and these are the added ones. So this is a lower bound. So there's 50 people who got their thesis using the Einstein Toolkit. We have regular releases, which is also good. Every 6 months or so, we have a new release that we throw out there that collects all the bug fixes and all the new features that we have. So you get a regular update of this thing without having to wait on someone's whims, roughly every 6 months. And we offer user support through various channels, emails, chat services, phone calls, video conferences. I think those are the main ones. Okay. So what kind of science can you actually do with the Einstein Toolkit? What have people done? Well, this is kind of a collage of pictures of results that were obtained with the Einstein Toolkit by different groups. The traditional one was binary black hole mergers, two black holes colliding. That was the initial one, but also the neutron star mergers very quickly afterwards. Supernovae, so exploding stars, were done. These are among the biggest simulations that were done with the toolkit. Accretion disk simulations, very, very important now after the kilonova events. Lots of groups are doing this. Has lots of interesting physics in there, but also more non-traditional ways in some sense. So boson stars have been simulated. Hairy black holes, theories of GR that go beyond black, theories of gravity beyond GR have been used by various groups that are in there. There have been searches for cosmic censorship. There have been actually cosmology simulations with the Einstein Toolkit. So it's a vast thing that you can do. And these are just the traditional ones, right? So you can also do other things. People have done some causal set theory with it, coastal modeling, and I think there was some really crazy ones, shrimp population growth. So it was done with the Einstein Toolkit. So it's flexible enough. All right, so, but it's not something that a single group or a single person even could do. It has always been a community effort from the very beginning. So we always had many individual persons involved in that, tackling a large problem. And that's a distinctive feature of the Einstein Toolkit. It's always been multiple groups. So why would you want to do this? Why would you want to go through the struggle of having to incorporate so many different opinions, so many different hats, so many different competing interests into one thing? Why not do it in your single group where you have one head honcho who says what we are going to do, and that's what's being done? That's efficient to a certain degree, but not if you face too many computational challenges. In fact, if you're doing this, you might feel a little bit like this gorilla here who's being given something that they're probably not quite understanding what it is. But hopefully there's a way that you can handle these computational challenges if instead of just one single person, you're multiple persons with multiple different areas of expertise. All right, so we want to do computing. It's kind of a basic computing device from a while ago. Ours are slightly more complicated, although hopefully easier to use. So if you look at what we currently have, or at least a while ago, these are typical things you would find in a supercomputer right now. Certainly lots of Intel compatible processors in there, but then also new processor architectures are being important again. This used to be the case in the past, but then everything was dominated by Intel x86. This is no longer true. There is ARM machines, and in fact, the second fastest supercomputer in Japan uses these ARM chips, lots and lots of them. And the fastest one uses AMD GPUs, actually. That's the Frontier machine that just came online in the United States. So there's many different compute architectures that you have to support, and you can't just say, I'm going to support only one because that's the only one I care about. Almost certainly you will have to support multiple ones because you'll run on a heterogeneous system, or you get computer time from one computing center, and you're lucky if you get it. So this is not something that a single person would do, because every single one of those is more than a PhD's worth of time to actually exploit properly. Right, and these things are obviously not small. This is a picture of the Fugaku system. So you're not talking about simulations on your desktop normally, but in a supercomputing center where things are inherently much more complicated. All right, so what do you want to do? We want to simulate cutting edge science using ideally the latest numerical methods that you might find in a paper that you have to implement efficiently and quickly so they can test them out before they are no longer the latest ones. And you want to make use of the latest hardware, whichever one develops faster. That means you have to have the ability to handle cache efficiently in modern CPUs. You want to be able to use vectorization options efficiently in all of these devices, and each one has slightly different options. You want to use accelerators, GPUs, correctly, or maybe FPGAs or other types of accelerators that might exist out there, you have to be able to scale to many, many cores, much more than we used to do. Now you have single CPU sockets that offer you 128 cores that you have to somehow use efficiently. And each core doesn't have a whole lot of memory bandwidth, but you still want to use most of them. You want to scale to many, many nodes. You saw these racks of computers. You want to scale to those, and it's very difficult to scale to thousands of compute nodes efficiently without being stuck and have one slow compute node in there that stalls everything. And of course, you want to keep up to date with the algorithms. Basic algorithms you can code up very easily yourself. More complicated ones, well, take more time. And for sure, if you want to compete on large supercomputers, you want to have these complicated algorithms because they will give you better answers, but they are more complicated. All right, so doing all of this on all the hardware is complex and tedious, not something that you want to necessarily do yourself. It requires experts from different disciplines. You want to almost have a computer scientist in there, somebody who understands hardware, somebody whose expertise is GPU programming. And beyond that, it always requires good data layouts and good APIs, which is not something that normally as a physicist we are trained to do, right? We have our physics problem, we throw it somewhere in and then we run it. Maybe that's just the wrong thing for the computer. In that case, you need to redesign your setup, have better data structures. In particular, data is really important. And then if you want to share this with others, you want to have an API that people can understand, that's somehow uniform across the whole thing and understandable to somebody who isn't you. I'm sure you understand your own API that you've designed. If you wouldn't, then it would be really bad API, but somebody else should do it. So that's one thing. And then once you have code that somebody else has written, you don't quite know what's the right answer that produces anymore. So you have to put in some automated tests that somebody who isn't you can check, does it produce the correct answers on this GPU, or is there some compiler change, some compiler bug that produces the wrong thing? So you have to have correctness in there that needs then to have some modularization of your system so that you can test what's going on. All of this should be done in a manner that's good now, but also good still 5 years from now. And let's not say 10 years, probably at that time you want to redesign, but at least for 5 years, you want to have something that's reasonably stable. So that for a PhD career, you have something that doesn't suddenly change underneath your feet. So there needs to be some thought put into how do you make things extensible, in which case it's useful to have expertise around somebody who's done this for 20 years. They probably ran into some of the pitfalls. You want to avoid reinventing square wheels all the time. All right, so a very simple example of how complicated this can get is this. This is what's called the domain decomposition that's used in Cactus. So this would be something really simple. You have a 1D wave equation. You have a string of numbers that represent data on the represent positions on the real line, and you want to split this into two processors. One processor does everything to the left, one processor does everything on the right. If you now have something like a finite difference stencil, you know that you have to look at neighboring points with derivatives out of these, which means that somehow in the middle, the processor on the left needs data that really belongs to processor on the right. So how this is normally done is by the introduction of what's called ghost zones. Essentially, you make a copy of the data on the other processor and you exchange them whenever it's appropriate. That's kind of the thing. You have a little bit of overlap between these and you make sure that this overlap stays in sync. If you do this in 1D, and if you were getting your PhD 20 years ago, you could get a PhD out of this doing this for a wave equation. And for 1D or maybe 3D, this is all doable. It's a little bit tedious, but it's a classic example that we now teach for how to use multiple processors. Here it's doable. And if you do it in 2D, it looks like this. This is still all reasonably understandable, but the real situation is more going to look like this. So now you have all kinds of mixtures in there. You have what kind of recognizably looks like square grids at the center, but you have two of those, not just one, it's all in 3D. You've got this funny overlap between these spherical coordinates here and then the Cartesian ones in there. Everything still is logically a square block, which is what you started off, which is what you know how to do. But everything has gotten much more complicated infrastructure-wise. And that's where the framework and the Einstein Toolkit helps you. It lets you concentrate on what happens on my simple block. You don't have to worry about the complicated interactions. That's really where the benefit is of any framework, actually. And they all work somewhat similar. All right, so back to my slide with the challenges. This is the same slide, this is the same gorilla. But now I've put in parentheses kind of our answer to this particular problem. So for vectorization, which is hard to code by hand because there's these different vector intrinsics depending on different CPUs, we have automated code generators, Crank or NeurP+. that lets you take the Einstein equations, which are usually complicated enough that most compilers just stop. They stop optimizing these things because they get too long. So we do this by hand. We give the compiler something that it more easily understands. That gives you vectorization, turns code that you can understand and it's slow into code that you cannot possibly understand, but is fast. So that's usually the challenge that you have. We want to scale to many cores on a single node. That's typically done with OpenMP. More modern codes might do this automatically for you, but that's the current solution. Scaling to multiple nodes typically uses MPI, message passing infrastructure or interface. That's usually abstracted away for you by the drivers, either QubIT or the new QubIT driver that comes around. So you don't have to worry, you really only deal with what's local. Normally don't have to deal with what somebody else is doing. We have adaptive mesh refinement, which is really complicated. There's drivers, QubIT, and then the method of lines for time stepping around. These are probably the most complicated pieces of software that are in our frameworks, and they are largely responsible for the performance of your code, at least once you go beyond a single node. So they're really important. You want to support GPUs, and while we don't have anything in the Einstein Toolkit proper yet that really supports GPUs nicely, the new driver QubIT does this automatically because it's based on this MREX framework, which is developed by the DOE, where they do have support for GPUs just because 2 out of the 3 big clusters that they have GPUs. So there you get it, and it works really nicely. But beyond that, there might be more things that you might have to consider. Maybe you will have to consider some sort of machine learning that becomes part of your simulation. So that's not so much kind of look at the answer, but maybe have a small machine learning part that runs along with your simulation and does something better than what you could do. Maybe it's a magic box that gives you better initial guesses for your root finder. Or maybe it's something that does the substructure for magnetic fields. Or maybe it's something that gives you, oh, this is a good guess for domain decomposition. But this is something that people are exploring. That is not something that we're normally familiar with, but there's lots of machine learning persons out there that might be interested in a problem like this. Or maybe you have to use FPGAs. Who knows? Hopefully not. You certainly will almost never have to design your own chip. There will not be an ASIC that you're going to use. But if we really do a million waveforms, maybe, or more crazy things, right? So who knows? But the Einstein Toolkit is in principle something that should let you do many of these things. All right. There's also more mundane challenges that you are faced. Things like, oh, how do you do your I/O efficient if you're running on 6,000 compute nodes? It's not a good idea if all of these start writing to a file at the same time. Typically, the file system, even on the big clusters, at that point stops working. And if you do this too often, you get a phone call by the administrators to tell you stop working there. So don't do this. We have efficient ways to do this that, for example, use better file formats, HDF5, or also just better ways of not overwhelming the file system. You want to checkpoint and restart if you run on anything sensible. Your simulation might run for 6 months. The cluster says you can only run for 24 hours at most at once. So you have to chunk up your work. After 23 hours or so, you want to write your state to disk, stop what you're doing, and then request another 24 hours. It's not hard, but you have to make sure you do it correctly and don't forget any bit of information that you actually depend on. So the Einstein Toolkit automates this for you. If you tell it, this is my state vector, it knows how to save everything to disk. There isn't anything like, oh, I forgot to save my random number seed. So all of my simulations are non-reproducible because I get a different random number all the time. So it does this for you. It has things like parameter file parsing. No longer are you faced with parameter files that consist of 100 lines of numbers that are uncommented that you don't know what it is. We have nicely written parameter files that have nice understandable forms and error messages and actually tell you what's log values. You want to visualize your answers with something that gives you the ability to produce nice pictures, yes, but also pictures that you can scientifically analyze and interpret, which requires proper file formats. You also want to be able to do analysis on your data, which is different from visualization. Like visualization is picture. Analysis might take a picture or might produce a picture, but you have much more quantitative answers for that. So QubIT, for example, lets you do a lot of the analysis as well as just the visualization of the pretty pictures. All right, you don't do this, but in principle, there is the ability that you can change how your simulation behaves while it's going on. It's called steering. You can change some of these parameters at runtime using a small HTTP server. And that's occasionally useful if your simulation is really not quite clear what it's doing. So you can look at a peak and say, oh, I need to change this, and you can do this at runtime. All right. So It's the time. Okay. So this is kind of the computational challenges. The other challenge that you will have is collaborative challenges. How do you make it such that you're actually collaborating properly and not quite competing so much as these gorillas do? So you have typically a scientific problem, and then you have maybe multiple groups with different problems. In some sense, this is the easy case. If they're not scientifically competing, they're very happy to collaborate on infrastructure. Very easy. So that's, if you have different groups looking at weather simulations or supernova down there or wind turbines, this is very easy. This is something that we can do and that we actually do have different groups doing that. Then you have a challenge, how do you handle computing in there? How do you collaborate getting best computing resources? How do you get the computing resources used efficiently? You want to build a community around your code that makes it easier to collaborate, so that it's easy for others to join. You don't have to already be part of some group that already uses it. You can come from the outside and join it. And we have that. There have been kind of a couple of groups that popped out of nowhere that started using the Einstein Toolkit. And that's the thing that you want to encourage. All right, you need to have a way of communicating with each other that doesn't rely that you already have inside knowledge whom to send an email to. In our case, these are the phone calls, the mailing lists, the chat rooms that we have, and of course the website where we try to make sure that you have a starting point where to look for things. All right, these are the basic ones. We use other software tools to enable collaboration between different groups. Version control systems for sure. Git is by now the dominant one, but there's others out there that you will still occasionally find. We make extensive use of ticketing system, be that GitHub or something else, so that there is a record, oh, there is a bug, and then somebody can fix that. And there's an easy way for you to submit a bug. It's not you submit something, tell somebody via an email, and then that person knows and nobody else. No, this is public. We have a wiki available for kind of quick documentation write-ups that we have. Currently, this is running MediaWiki that is used as an alternative to the website mostly. And we have these regular workshops, at least once a year. We have one in the United States or in Canada, I think we had one. There's a complementary one usually in Europe, about a couple months before or after. There's one this year, end of August. Right, so now you have these groups, you try and make sure that they collaborate nicely, and it mostly works. Sometimes, of course, you have many, many groups that are all working on the same scientific problem, which makes it then harder to collaborate because they're obviously competing for the science results. This was something that the Einstein Toolkit has faced from the very beginning. In fact, it was designed to do that. That's why we have these modules in there that allow people to have some of the code public, but also keep their own science code private, either for a while or forever. But that's a design goal. And in fact, it's a feature that we don't want to miss, because that way you can spend a couple of years or so developing a really good code, get your science results out there without somebody sweeping in at the very end and publishing the results, while still having a path of making everything public afterwards. And that has worked surprisingly well so far. I find that while there is, of course, competition, most people are reasonable what they want to do and what they're willing to share afterwards. So this has worked quite well, and I think this is a big success story. Right. We tend to encourage standards to make it possible for different groups to collaborate. This might be using standardized file formats, for example, HTML5, rather than everybody home cooking their own ASCII file format all the time. Right, so there's HTML5. We provide a set of tools that you can use. Traditionally, when you look at what supercomputing languages were, what it started with Fortran, and then C and C++ joined the arena, and nowadays, a lot of more modern approaches really require C++, not the most fancy C++, but C++ usually. In principle, there could be also other languages that could be used. Maybe not so much Perl for HPC, we certainly have Perl for all kinds of tools, but Python could be something that could become popular, at least for Glue. And the Einstein Toolkit, in principle, would support these. The ones in there are currently C and Fortran, but there's no strict requirement. This just happens to be the one in there. In fact, there have been Python bindings to the Einstein Toolkit before that somebody experimented with, and they are still sitting on some server at LSU, I'm sure. No, that was Oleg. That was Oleg. I did not left nothing at LSU.
Yeah.
Okay. Yeah, so that is possible. So it's not limited to that. All right. Also, different operating systems. For sure, the big ones right now are Linux on the clusters. All clusters run Linux. But on your laptop, it's a bit more varied. People might run Linux, laptop workstation, Mac OS. There's lots of Macs in here. Windows is also becoming more popular again, either just for Windows itself or the Linux subsystem. So there's different architectures that we want to support and make sure we use them efficiently. In the past, again, there used to be more. There used to be a galore of different operating systems. Thankfully, I never had to deal with them. But this is important. It also means that our code is more portable. While I personally don't care so much if it runs really well on a Windows workstation, I care that I can compile on a Windows workstation because it makes it more likely that it compiles on the next exotic version of Linux that I have to run. All right. Important also, we want to give credit to whom credit is due. So the Einstein Toolkit has a DOI where we say, cite this. If you use the Einstein Toolkit, we collect authorship information of all the contributions to the Einstein Toolkit. We try to have ways that you can say, if you contribute a bit of code, there's a standardized way that you can say, if you use me, please cite this paper, please cite that person. That we automatically collect and show on the Einstein Toolkit website. And maybe by the end of this hackathon, it will also be possible that your simulation tells you at the end, you've used methods A, B, C, D, please cite these papers. Not terribly difficult, but really useful to have. All right, that's about it. Just to show you who was involved in their collaborative challenges. This is always a little bit out of date, but researchers in the United States, this is a subset of all the groups that have contributed to the Einstein Toolkit, just in the United States and also internationally, and many, many more that I haven't listed. So we have had lots of contribution. It also moved, right? It used to be that it was centered at NCSA initially, then moved to Germany, then moved to Louisiana, then kind of spread out. Now Zach's group has been very active. So it has been something that has had sustaining power. It's not something, oh, it was developed by a group, the group retired or did something else and the whole thing died. It has been resilient towards that. All right, that's almost it. I'm not sure how many more slides I have. Just to summarize, what's the goals of the Einstein Toolkit? We want to be a community-driven astrophysics infrastructure that provides 4 computational tools for numerical astrophysics, but it's also a general purpose tool. So community-driven is important. There's big components in there. Certainly Cactus historically has been the largest one. That's the computing infrastructure, the workhorse basically, but also simulation factory that lets you run on different clusters, that just collects how do you run and compile on different clusters. Code generators, Crank and NeRP, and then science modules that people have contributed to it. There's a couple of guiding principles. It's always supposed to be open, community-driven, has good interface, and we don't want to do things in backrooms. So everything is always open. We can tell why we make decisions when we make decisions. We want to provide production-ready codes, so we don't get just a little bit, but everything from beginning to the end. And we want to provide high-quality code that's well-documented and is reasonably easy to use. All right, so this developed historically from just a kernel, say, of Cactus codes that people had written to make different GR codes actually work together. And then it accreted extra modules, created an accretion suite that plugged in there, got larger because now you have something already works, so you get better return of the infrastructure if you invest in this. So it's kind of a positive feedback scheme. You get more different types of fields of science. Maybe it was just black holes. Now you get the neutron stars, you get the supernova, you get the boson stars that plug in there, that make use of lots of things that you can still use, even if your physics is actually different. Most modules, again, are open source, but not all of them. And again, this is good. This is by design. This is not a bad thing. We want this. All right, so how do we facilitate this? How do we facilitate in particular interoperability? We do this by having a couple of base modules. As an example, this is the Einstein equation with the source term on the right-hand side. We would have space-time curvature here, and then something that handles the constants in there. Maybe your version of C changes, hopefully it doesn't, but your version of G may change because G is not a particularly well-defined constant of nature because it requires actual measurements. So then there's something that gives you matter. This might be fluids, this might be something else, might be hydrodynamics, maybe an electric field, maybe scalar fields, maybe actually particles, radiation, God knows what else. Different things going on. This is the physics. If you map these to computational elements in the Einstein Toolkit, then we have ADM base, which encapsulates just the metric. and then your different metric solvers can plug in there. And as long as they plug in there properly, everybody else can use them. It doesn't have to know about your metric solver. Don't care, as long as ADM base is in there. The same thing for the matter. There's TMNU base, which gives the fluid or matter thorns a way to tell the geometry. This is how much matter is in the system. We then have actually evolution thorns. For example, the McLaughlin code, MLBSSN, will couple to these two, the ADM base and the TMNU base thorn, to get its information. Similarly, there's a thorn called hydro base, which is responsible for the fluid and provides a unified interface for the fluid dynamics, so that Illinois GMHD can use that, so can GeoHydro, so can the new features that are in QubIT. And then there's GeoHydro, one of the evolution codes that then kind of ties into everything. But these are not the only ones. We have initial data and analysis codes that typically only interact with the base ones, so that everybody else can use them. And then we have variety. We don't want to have just one. We have by now at least 3, I guess, different GR evolution codes, the McLaughlin one. Then there is the Dean public code, and there is BICAR, all in some sense do the same thing, but slightly different, with slightly different goals and slightly different capabilities, actually, and also different ways of readability. Lean is very easy to read, it's handwritten Fortran 90 code, while the other 2 are generated by code generators, so harder to read, but maybe either have a lot of history. McLaughlin has been well tested, while BICAR is much newer, it's based on NeurP, so it's generated by Python, easier to use, than you don't need a McLaughlin, you don't need a mathematical license. Same with the GR codes here. GeoHydro was the initial one, developed in the European Union, then made open source. Illinois GMHD is a successor of the probably 20-year-old and really well-tested Illinois code that Zach rewrote and then made public. So there's different options, they can do different things. All right, I think I went over these already. The Einstein Toolkit provides you tools. That's what it does, it's a toolkit. It doesn't, unfortunately, provide you with insight how to run the simulation. There's always a kind of a gut feeling, how does the simulation behave? What do I have to do? Things that you get after 10 years of doing it, we can't give you that. But we can give you more time to develop that, because we can give you the tools to try things out. You don't have to spend your time, why does my code not work because I've got the wrong semicolon? You can at least worry, why does my simulation not work? Why is it physically unstable, rather than I've got the algorithm wrong. I think that's about it. Once more, credit and citation. It's all free and open source, as in beer and as in speech. There's no requirement actually to cite anything. If you want to use it, you can do so. We can obviously not stop you. We do request citations for the Einstein Toolkit itself with an ever-changing GUI. So each release gets a new one, so that the persons who worked on that get proper credit. This, I think, is the perpetual one that always updates to the newest one, but you should cite the one you actually used. You can cite the Einstein Toolkit or the Cactus papers, and certainly the papers that are on the list of tools that you actually use. Right, I think that's basically what we have right now. Let me give you a quick vision what we want to do in the future. So the big new thing right now is that we're working on a new driver thorn to do MPI more efficiently, QubIT, that uses the MREX infrastructure developed by the DOI, that will hopefully let us benefit from that work. QubIT was basically a one-man person. A one-man project was developed as a PhD project by a student at Penn State and in Tübingen, I think, and has been the workhorse so far. This has many more persons working on it, so it has the ability to use more features. It also supports GPUs, which we never could before. There's spherical coordinate thorns being developed at RIT, and Zach is involved in these. So these are new because they get you better efficiency, because you have coordinates that's really now adapted. Python code-based generator NeurP Plus that is slowly developing to be as featureful as the crank-based one. Some things it's already better, some things it might not be, but for sure it's easily extensible, and it has an active community that drives it. While crank is working, but it's harder to maintain because the main developer got hired to do something else. We have more than just Cactus codes in the Einstein Toolkit now. We have the Self-Force 1D code written by Sam Kapp and Peter Diener that lets you do something completely different, but still GR. And that will now soon have actual curve background support, and we'll see how quickly that will happen, but this will be the next big thing. Very recently, we added a PN-based initial data and eccentricity reduction code to the Einstein Toolkit, so that goes towards the full thing, from this is what I want to do to getting the plot out of the simulation. We have new declarative syntax in Toolkit, the presync code that was in there that hopefully catches errors. And we have Python-based simulation analysis in QubIT that gives us the last bit. So now we hopefully have everything from beginning to the end, and we can show you examples how you can do everything using just Einstein Toolkit. All right, in summary, there's the Einstein Toolkit website, kind of the first place to get help. There's also a big help button there. And that's mostly it. Any questions on anything that I said, anything that you're curious about, or anything where you want to contribute? Yep.
Why is it called Cactus?
Oof.
So the idea was that Paul Walker, who was the original creator of this and was left relativity many years ago, he had this vision of the cactus plant as a metaphor, right? With the cactus flesh being the core infrastructure and then the thorns being the modules. And of course, we've learned since then that cactuses don't have thorns, they have spines. But if you're not a biologist, you might not realize that distinction.
And somewhat the proposal renamed the thing Rose never quite caught track. Anyway, yeah, so I think it's just a cute name.
Hey, back then we used to say gravity waves all the time too, which is also not correct.
All right. Okay, then I guess I have an hour and a bit left, right?
I think so.
Which is probably way more time than I need, but I can always give you a bit more details. So, so that's kind of the presentation part, where I just want to give you, this is the lightning fast review, although it's not so lightning fast as I sometimes hope, but at least it gives you a bit of an idea of what the toolkit is about. So the next thing now is I want to actually show you what a simulation looks like using this tutorial server. So as Zach has already alluded to, and as I've already said, we have a toolkit server that you can log into and then run it. So if you haven't done so yet, please click here on this link. Yes, and then you will be presented by a login mask that I can't show you because I'm already logged in, but you can enter your username and password. If you do so, you should be presented by a page that looks like this, basically a standard Jupyter Hub interface, which shows you different files. And the one we care about for today is the one that's already open in green. If you click on that, you will be presented by this particular setup, which is a modified copy of our tutorial notebook that we use for new users on our own server, but also here. You can also run this on your own laptop if you want to. This is what most of these prerequisites are about. So it's also a good source if you want to install the Einstein Toolkit on your laptop. And it has one of the not too exotic operating systems, and you haven't used it for 5 years yet, messed it up beyond repair. This might give you instructions how to install it. We have everything from macOS to different versions of Linux to Windows 10 and 11 using the Windows subsystem for Linux. So it's Linux in disguise, but you can run it. Okay, none of this is something that we need because we have our own server where everything is nice. So what I will do is I will in some sense just click through and talk a little bit of what's going on. There's a bit of exotica in here where we make sure that the notebook server is actually easy to use for you. This is to some extent. Yes. Maybe do this. Oh dear. Is this better?
Much better.
Okay, so this is just specific to this notebook. At home, you wouldn't do this. This is just to make the notebook work more easily and be a bit more nice. So let me execute this. And as you will see by default, this is a Jupyter notebook. So the cells are by default just Python code that you can execute. There's, however, tricks that let you execute shell commands, which is actually what most of what this does, is by putting this %% bash sign in there. And that instructs Jupyter to execute the remainder of the cell as shell commands. So we're basically telling you what you could enter into a terminal, but you can pre-populate the cells with what you enter, and you can just press Shift Enter to execute the cell, and you get to see what it does. So the first cell is actually a trick. Compiling the Einstein Toolkit on this particular server takes about an hour, which is way longer than we want to spend. So what we've done instead is we've provided a pre-compiled version of the Einstein Toolkit that we've seeded somewhere in there. And this rather complicated line of code, which if you don't understand it, don't worry, takes this pre-compiled version and extracts it into your home directory, assuming you haven't done so already. If you have, then you get an error message, which is by design. We don't want to override something you already have in there. And I'll click on that. That's probably actually the slowest cell of the whole repository of the whole notebook right now. So you can see it had a star for a second. Now it's done. It has extracted everything. Once we have downloaded it, so to speak, we can actually use it. Here, it goes through the motions of downloading it. You can execute these cells. Nothing bad will happen. It detects what's already there and only downloads what's missing. And since nothing is missing, nothing gets downloaded. So first, we change to my home directory, which here is /nsf/home/my username. For you, of course, it looks different. And then we use a tool called get components to actually download the Einstein Toolkit. So because the Einstein Toolkit is developed in a distributed manner, we don't have a single Git repository that you could just clone and use. That's really good if you want to actually have different persons contributing, because there's no central arbitration that kind of blesses what goes in. You can put in whatever you want. You can make any combination and then download them with this get components. The downside is we actually have a couple dozen Git repositories that make up our Einstein Toolkit code. So you don't want to download them by hand. Get components basically just takes a list of Git repositories and downloads each one after the other and puts them in a certain sane arrangement of directories. So that's what it does. If you look at other big code repositories, they are similar. I think the Android code does the same thing. They have their own solutions. We predate them. So that's about it. So get components is just a script that downloads them. It's written in Perl. But you can see if I execute it in here, it tries to do something, and almost certainly it just says nothing needs to be done because everything is already finished. So it was really quick. What it does is it creates a object directory called Cactus where all of my source code lives. And everything in this tutorial almost everything will live in there. Contains all the source code, all the extra software that we will install is in there. Once you have it, you have to compile it. You have to somehow tell the system, though, what your computer looks like. Is it a Linux system with this many cores? Do you use this particular MPI stack? Do you use this MPI stack? Do you have this software installed? Do you not? This is complicated. SimFactory, however, is a tool that we use to automate this. It also abstracts away different clusters so that you don't have to know how to submit a job on different clusters. It doesn't have to know if this one uses the old PBS-based queuing system or the modern Slurm one, or how the queues are named, or what's the maximum runtime, or God knows what else. All of this is packaged for us in some set of documentation and database files that you can also edit, of course. But it simplifies it. So you can also use it on the laptop, which is what we are doing here. So on a laptop, you can guess most things. There's the setup silent command in the SimFactory tool, which when you execute, tries to guess what your workstation looks like. So it figures out how many cores you have and your username, and then writes a very simplified documentation for that. So if you look at what it says it writes the output to this. Oh, it's not even in there because it was already done. So in your case, it should say one more line. It should say written to a particular file, which I don't have because I ran it for the second time. I cheated. But that file you can open. It's just a text file, and you can see what's in there. Sometimes you have to edit it, but it should say what's the actual file. Right. So any questions? Am I going too fast, or is anybody actually clicking along? No clicking along. Okay. All right, so now you've got the Einstein Toolkit. You've kind of set it up so far that you somehow familiarized the build system with your cluster. Now we want to actually compile something. The Einstein Toolkit has about 300 different modules that do all kinds of things. Chances are you're not going to use every single one on every single one of your runs. So you don't want to compile them because it makes it slow. Instead, what we're doing here is we're constructing a minimal list of these thorns, these modules that let us run the two examples that I want to run. I want to run here a simple hello world example, which is described in a parameter file called hello-world.par. And then the TOV example, the single star that I talked to you about before. So these are the two parameter files, two simulations that I want to run. We have a tool called make thorn list that takes as input the kind of full thorn list of everything that's available, called a master thorn list here. And then what you want to run, in this case, these two parameter files, and you give it an output where it says, in there, write a thorn list that's just large enough to let me run these things. Execute this, takes a bit. And now you would have a new file that's now faster to compile. It makes it faster. It also makes a smaller executable. Generically, what you want to do. Okay, so now we have this. Now we can actually compile it. SimFactory, the tool that manages our clusters or our workstation, knows how to compile the Einstein Toolkit given a particular thorn list. So this is the thorn list that we just generated, written to that file. It takes an option -J if you're used to make. Make has the ability to compile in parallel, takes an option -J for jobs, to say how many parallel compilers do you want to start. Each of you has access to only a single core on that server, so putting anything larger than one really doesn't make much sense. So I just put in one. You can also leave it out, in which case it uses a default. If I press enter, it goes through the motions of compiling things, but really doesn't have to do anything. Let me show you what it's doing. You will see that it scrolls to the bottom and over shows you what's going on. And that's a little bit of JavaScript code. And in fact, it means that if I want to scroll upwards, it's going to actively resist me. Instead, you have to click on that little checkmark button here, which disables the scrolling. You see it doesn't scroll anymore, but now it lets me scroll up and show you what it's actually doing. This is a typical Cactus compile stage, where it will first tell you what it's compiling. By default, it compiles what's called a configuration called sim, basically a set of thorns. You could have different ones or different names based on the same source code, which is sometimes useful. And then it tells you what it's going to do. Currently, I'm compiling version of Cactus 4.12, which is the current release, and that will update every half year. And then it kind of tells you what it's doing. It's reading the list of thorns. And once it has these, it knows what thorns to compile and gives you some output what's in there. So apparently I have a TOV star, which has gravity in there. So I need to have this ADM base module, which had gravity in there. Turns out that this ADM base module actually requires something else. It requires some notion of coordinates provided by the CardGrid 3D module. So that's also output. So you get a bit of information what's going in there and why this is in there. It goes through them all. You can see it's not really a short list, even for something that's fairly simple simulation, actually. But then it goes through and it says, oh, I'm going to parse through all the files that describe the modules to me. There's a file called interface that describes what a module provides. We will learn about these when it comes about writing thorns later on, today, actually. And then also files that describe what parameters do these modules have. For example, an initial data module might have an option to produce initial data for a TOV star or for a single black hole. Or the method of lines module, which does time stepping, might have different methods that you could use. You could use just a classical Runge-Kutta 4, or maybe something else, maybe an RK3 or an Adams-Bashforth method. These are all runtime parameters for us. Very little in Cactus is compile time fixed. You can, if you want more speed, but you typically don't have to. All right, let me scroll to the end. Where? I think by now it's done. So somewhere here, we will say checking status of thorn, and nothing ever happens because all of these modules have already been compiled. And you get one long line where it says it's linking everything up, when it says creating cactus_sim, the name of the executable, based on all of these thorns that were linked there. Then it will say it's done creating cactus_sim. And then it does one more step. There's a couple of helper utilities that we're providing you that just lets you do useful things. For example, lets you combine multiple output files, splice multiple output files, split them. This make thorn list thing would be one of the tools, only it's Python, it doesn't need to be compiled. And then you're done, it'll say done once more, and you're good. All right, so now we have our executable. Let me actually check if everything worked. So the simplest thing you can always do with computers is make them say, hello world. This also exists in here. What? No. Ah. Clicked on it again. We have to wait for a minute. So we want to then run the hello world example. I can't. Unfortunately, the moment I say compile, it deletes the old executable. So I can't just abort it. I really have to let it run through for a second. So you can see that actually the link step is relatively slow because it is still a fairly large executable. Okay, so it's done. Let me do the next one. So let me run Hello World. In SimFactory, there's an abstraction layer that lets you do these things. There's usually two steps. You first create a simulation that you want to perform. That sets up a skeleton, puts in the parameter file, kind of tells what you want to do. And then you submit runs or segments against that particular simulation that you've created in case you want to do this multiple times, maybe one day, next day, next day. For convenience, there's usually something that combines both. In this case, it's the create run command that tells you create a simulation and run it right away. In this case, I want to create a simulation called Hello World. I want to use a parameter file that tells Cactus what to do that's located in this path. That's the standard way that you would always do this. If I run this, you see it gets a star. Why is this not in there? Oh, it already exists. Oh, my fault. So let me do this. So I ran this before, and then of course, if something already exists and I say I create it again, it will legitimately complain and say, don't do this. So now I'm just going to get rid of it. And let me do this. So now you can see it creates the skeleton and it starts running, and it's so quick that I can't really show you what's going on. But you can see that at the end, it outputs hello world, outputs this 10 times, and then it quits. And as long as you see that, then you have a simulation that actually an executable that worked. There's interesting output up front, if you care about that, where Cactus kind of tells you what's going on. There's information from SimFactory here. Then this thing with the plus is just a shell telling you what it's going to do. And then starting with this nice looking Cactus logo, this is the actual Cactus one. And if you do a simulation, you may want to check what it's doing. It tells you what's called a schedule, how it executes things in which particular order. Here, this is very simple. The only thing that we have in there is, if I can find it, is the hello world module, which runs its hello world function. Pardon me.
Someone has tried 10 times, or they just print 10 times.
Because by default, if you don't tell it otherwise, Cactus will execute the evolution bin 10 times. Could have been 42 times, but it's 10 times. That's the only reason why. Each time it executes that function, says hello world, it gets executed 10 times. That's where you get 10. So the nice thing here is that with all of our modules, we can't really tell in advance how things are necessarily going to execute. All we can do with our modules that are independent, you can say, I want to execute, for example, the thing that prints out the maximum density after the density has been computed. Or you can say, I can only compute the density once I have my metric. But you don't really say in advance, first to A, then you don't say A, B, C, you just give this relative order. And Cactus here prints out what is it actually going to do in the absolute order. And every once in a while, you have to check that it's doing the right thing and not accidentally got things wrong. For example, if you have a typo and you tell it do something after the metric has been computed and you want the metric, then this is not going to work. It's a computer. It doesn't know what you want. It only knows what to tell it. So these can be helpful. But you can also see that even for this, it's relatively lengthy and pays off for large simulations. All right, so this seems to work. This is a very simple one. Now let me do my single star simulation. This is a really cut down version of what we would normally do. It contains what's called a parameter file that's already in the thorn list, already in the tutorial notebook, so you can see what it is. You can see it's relatively straightforward. It normally has the form name equals and then some values. For example, here would be the name cactus : terminate, which would set an option called terminate of the actual Cactus infrastructure. It sets it to the value of time. This would tell it that in principle, you want to terminate once your time counter has reached the value of 400. And then it would stop the simulation. In fact, this will stop earlier because a later limit will say only a minute. But these are the ones that you have. There's documentation on the website that lets you figure out what all of these values are. For example, for this termination trigger thorn, which will be the one that kills me after a minute, that will do the right thing. So let me execute this. And this cell is a bit strange in that it really just calls the cat command and it writes the content of that cell to this file. Run this. It's quick. And I'll have to do my RM again. Simulations. This guy. Right. So this is now a slightly longer sim factory line. Yep. Yep. Here I've done just a create. So this is no longer the combined one. This just creates a simulation. It gives it a name, TAV-ET short. I've been explicit. I've told it use the simulation, the sim configuration, not just the default, which happens to be the same, but this is explicit. Then I do trickery. Forget about this replace thing here. That just limits the runtime to 1 minute. It used to be set on remaining wall time is set to 0. That means run for however long it takes. I don't want this. It runs for half an hour, so I limit it to 1 minute. Now, if you don't understand this, don't worry, you're hardly ever going to need this. Normally you do this by hand, you edit the files. I just need scripts. But the last one just says the parameter file to run, and that's the one we just created. So let me do this. Let me execute this. So the output looks very similar. It says this is the parameter file. It creates the skeleton. It creates the job directory. There's an executable. And there's the parameter file. Nothing else happened because it doesn't run anything. It just creates the skeleton and puts in some files. Then I have a separate submit command here that needs to know the same name. It's going to run this particular simulation now, not something else. How many cores do you want to use? 1, because that's all I have really. Use 1 OpenMP thread. Only have 1 core. I don't have many other choices. And run for at most 2 minutes. So this is where this comes in. So this is the limitation. If I exit this, you will now see it says something. It assigned a restart. It executes the command. And it is submit finished, and there is a job ID here. If this is on a cluster, then this job ID is the ID that the queuing system gave to your system, to your job. On the workstation, this just happens to be the process ID so that there is a recognizable number. So this is now running, and I can prove it's running by listing the simulation that are ongoing like so. I'm doing this a bit quickly so that I'm done before the 2 minutes are over. So list simulation tells you all the simulations that you have on the system. I have 1 apparently. TAV-ET short, which is active and running in my first restart, and it has the same job ID that is just barely visible up here. So that's my simulation running. If you want to know what it's doing, SimFactory has a command called show output, which tells you what's going to be spit out on standard out. If you execute that, then quick enough, again, it will show you what's going on. Oops, shouldn't this scroll? This is so quick. So you can see where it was running. It would run with 1,130 time units per hour for 400 time units. So that's still about half an hour or so. So I didn't want to wait. And you can see that it was stopped by its termination trigger because it took about a minute to run, and that's when I say stop. So this isn't the full thing, but it shows you the motions that you go through, and it shows you the actual output that you would see. And once this is done, it stops printing output to screen, and we are basically done. So this is kind of going through very quickly what it's doing. You can do more with the Einstein, with the simulation factory and the Einstein Toolkit. You can actually manage your simulations. You already saw my list simulations command. I call this again, this time without any options. Actually, you see that I actually have 3 simulations going on in the system. There's the Hello World one we created first. Then there is the TOV short we just ran. Then there's a mystery one, which you haven't seen before. That's called TOV-ET, which is just a long version that I ran before, and I stuffed your home directory with the data. Yep.
I don't have that.
You don't?
I don't have the TOV.
You don't?
TOV, no.
Really?
Where is it supposed to be?
It's supposed to be in the tar file.
Which tar file?
The zip file, actually. So you don't have it.
Which
the one that has the source code should have also had the simulation structure.
You mean the tar.gz?
Yeah, the one that we're unpacking, yes.
So that would be under Cactus then. It wouldn't be under simulations.
No. It goes up one directory.
I have it.
You have it?
Yeah.
Oh, Steve, did you get a fresh setup of the system?
Yeah, I did it. I did an RM-FR.
And then you logged out and back in? Okay, so if others have
an RM minus FR cactus directory, but not this, but the simulations, when I got down to Hello World, I did an RM minus FR with simulations because I couldn't run the world. And that's where it was.
Okay. So stay away from RM RF if you don't know what you're doing.
Now I didn't realize that's how you did it.
Yeah, it's a mean trick.
Yeah, also it's called cactus.tar.gz, not cactus and simulations. So.
Yeah, we had to change for things. Come on.
There's a number on computers exact.
Yes. So anyway, so you should have the data. It would let you things. So this is kind of the one that's a harmless command. There's also a command to stop your simulation, which we've commented out so you don't accidentally do that. And there's a command to delete the simulation if you don't need it anymore called purge. Again, commented out so you don't accidentally delete your very first simulation on the cluster after you tried things out. Pardon?
Why are you giving us the warning about the?
So the queuing system doesn't tell you all the information. Ideally, I would like to be able to tell it, has this job with job ID finished? And the queuing system just doesn't tell you. The only way that I can tell that a job has finished is if I ask the queuing system and it's not there anymore.
And there is no queuing system.
There is no queuing system. Then you kind of get this warning where it says, I have an unknown job status U, and then later on it interprets that as, yeah, this just means the job finished. It's a interface bug. It shouldn't do that. Yeah, it's expected, but it really shouldn't do that. We should fix SimFactory to not do that anymore. Right, so that's basically it. So I talked a little bit about the output being generated, and you saw me deleting some things when I had my simulation already started. I know where it is because I set it up. You can also ask SimFactory, where did you actually stuck my output when you ran it? There's a get output there command that you can run, and that then prints to screen where it is. On your laptop, it's always going to be home simulations, blah. On the clusters, it's normally somewhere in the scratch directory that the clusters have. You might not know where this is, in particular if you're using SimFactory, because, well, the goal of SimFactory means you don't have to know every single detail of everything of the cluster, but if you want to get the data, well, how do you get to it? This is how. You can query where it is, and it will tell you exactly where it is. All right, so that's the data. Now let's do something a little bit more graphical with it. Let's actually plot some of the output, and here we're going to use QubIT. That's very new. I think this is only part of the tutorial since this release, while QubIT has been in the release for 2 releases already. So QubIT is not directly available if you download the Einstein Toolkit, mostly because it's a Python package, so it has its own dependencies which we don't want to manage. There's pip that already does that. You get a version of QubIT, but that's only in there for the documentation. To actually use it, you have to install it via pip. And here, I'm doing a bit of a trick. I'm setting what's called the Python user base environment variable, which means Python is going to install everything into the subdirectory of your Cactus directory, so that if you don't care about Cactus anymore, you can just remove it, everything is gone. You're not polluting your home directory with stuff you don't care about. So that's what this is doing. Otherwise, it's a standard pip install command to install the user. And I guess capital U is unsigned, or whatever does it stand for? Upgrade. Okay. And we tell it exactly which version we want. We want version 1.3.4 because that's the one that belongs to this particular Einstein Toolkit release. So if I execute that, almost it's not going to do anything because just the text is already there. If this was you, you would see that it goes through what it has installed and then installs whatever is required. And again, there's trickery in the notebook to make this work. But if you enter the commands as they're shown in the cells in a terminal on your laptop, it will also work. If you enter them as they are shown in a notebook that doesn't do the trickery, probably not. But you have to look at the trickery at the beginning. Okay, so now we have it installed. Let's actually plot something. The examples that Gabriele provided is something that just plots the maximum density of the center of the star, actually. And also then a 2D plot that shows you what's the density distribution in your star. So let me execute this cell. And you can see this is still just bash commands. So these are utility helper programs, scripts that are provided by QubIT that let you do common things very quickly. So you can very quickly plot just a time series of data, which is located in the data directory of my simulation. And if you're eagle-eyed, you will notice that I actually use not the _short, but the actual simulation with all the data. And I've just hard-coded the path because this is what you would normally do. There's a way to do this programmatically, and you could do this in the tutorial notebook server, but they look too ugly for me to actually show you, and you wouldn't do so normally. So this is what a normal sane person would do if you went to computer. The variable you want to plot, is the variable rho, the density. We want to do the maximum reduction that was computed by Cactus while it was running. That's the maximum value. And then it takes an out there option to tell it, where do you want me to write the output? In this case, it's just a PNG file of the plot. And the same with the plot grid var script that actually produces a pseudo color plot of a certain subregion, in this case, of the equatorial plane data. So let me execute these two. Let's see if they overwrite the complaint. Come on. So you can say this is going to take a little bit, apparently. Yeah, it's the slowest thing on these systems is actually the I/O, it seems. So I'm not sure if I'm quick enough, I can probably show you the answer while it's going on. Oh, there it's done. So it wrote the PNG files. If you're on your laptop, of course, you just open a PNG file with your favorite image viewer. This is a notebook. I want to show you what's going on. So I use a bit of Python trickery to create a Python image object that loads the generated file. So this is the file name, I load it, and then I show it in the display. And this is what you get. So this is the density over time at the center of the star where it's maximal. So you can see it gets a nice label. It gets a unit in here. It's 10 to the minus 3 in what's called geometrical units, which is roughly for a neutron star. So we're talking about 10 to the 15 grams per cubic centimeter, actually. And then there is a time column, which shows you the a measure of time that has passed over the simulation. And you can see we start off with a density, then it starts to wildly oscillate for a bit. And if I were to let this run for longer, it would eventually settle down to a stable value. So what this means is we take our spherically symmetric star, which in theory is a stable solution of GR, so nothing should change, but you put it on our grid where it actually is under-resolved. So now the star on the grid is out of equilibrium. We let it go, and it's like as if we kick the star a little bit, so it rings like a bell, and that ringing is exactly the oscillations in the density that you're seeing. While the cause of the oscillations isn't physical, because it's under-resolved. The frequencies is physical. There are eigenfrequencies that the star has that it will ring if it is somehow excited by other means. For example, there could be tidal interactions that starts ringing that star. These are fixed, and you can check that they have the proper frequencies. Probably not with that coarse resolution, but in principle. And this is actually something people do. It's called astroseismology, and it works on that principle, just presumably much more complicated. Right, so that's one. That's just a line plot. We can also do a plot that shows you the density of the star on the 2D plane. And that's this thing here. You see it labeled X and Y. Our star is roughly 8 or 10 units large. The unit is about 1.48 kilometers. So that's about the size of the star. And you see that these squares, each square is a single volume element of our resolution. So it's totally under-resolved. Completely, totally under-resolved. This is completely unphysical, but it runs in 10 minutes and it doesn't crash. So you get to see at least what the data looks like. And of course, if you had more complicated simulations, you could do that. You can also add these to a script and then, for example, run it every 10 hours or so, and then update your output of the simulation on a web server as the simulation is going on, and therefore monitor what your simulation is doing. This is very useful very often. Just have a picture, see if you have two neutron stars, how are they evolving? Are they actually spiraling inwards, outwards? Are they doing something crazy? But this is scriptable, so you can easily do that. All right, so this is with scripts. QubIT, of course, is, yeah, I have left time, yes. QubIT, of course, is in Python. So you really should be using it from Python, where you have much more control over what's going on, rather than just the scripts. The scripts are convenient, but they let you do one thing, and they do this well. But in Python, you have more control. So let me show you what this looks like using QubIT as an actual Python command. So this is now, I think this is the actual first Python cell in this notebook. So we kind of abuse it, but it's working here. If you've used Jupyter notebooks, you're probably familiar with this matplotlib magic that tells it that you actually want to plot things on the screen rather than popping up an extra window, which your browser won't let you. Then we load just matplotlib for plotting, and then QubIT modules, QubIT SimDir, which is an abstraction layer for the data that's generated by your simulation. It gives you information what's produced, and lets you open individual files. And then QubIT visualize matplotlib, the basic visualization module that QubIT has that lets you use matplotlib as a backend. There's a 3D one. Is that already? Okay. So there's other backends that let you do more fancy things, and of course analysis. So this is what you would be getting here. So let me execute this. Oh God. So so there's a bit of explanation what's going on. SimDir really represents the main simulation directory. This is a little bit bad didactically because I'm just using that variable data there that you really haven't seen before. It's defined 3 cells up somewhere sneakily where you didn't see it. It is home simulations TRV-ET here. I should have probably spelled it out again. But you give it where your simulation ran, where the output is, what SimFactory told you more or less, and then you generate an object in Python that represents the context. If you print this thing to screen, oh, great. What did I do? There. Probably skipped this cell. Yeah. Okay, so this was what was there before, and then I messed it up, and now it's back again. So it gives you an overview. What do you actually have? What time series do you have? Say for minimum, apparently I have got a time series called H, which, if you look it up, will tell you it's the Hamiltonian constraint that essentially tells you how close are you to the actual solution. We had Miesner's comment on saying, hey, if you start with initial data, it doesn't satisfy the constraint, either the computer breaks or the programmer shoots itself or shoots themselves. This is the one that's monitored here, where we make sure that, in fact, our simulation does satisfy these constraints at the beginning and forever after. The one we care about, of course, is the maximum one. And we want the maximum of our density rho, which is here.
There's someone raised their hand.
Oh.
Maybe you want to.
Yes, if you can unmute yourself and just ask the question, please.
What is exactly the difference between the minimum, maximum, and norm time series?
So minimum, maximum, norm 1, norm 2, they're all reductions in the sense that they take the whole grid and they reduce that to a single value. And then minimum time series means the time series of the minimum values of that particular value over the grid over time. The maximum is the maximum of that variable over time over the grid. And then norm 1 is the P1 norm or L1 norm, I guess. Basically the absolute value summed over divided by the number of grid cells or something like that. And L2 is your Euclidean norm that you would see in math, and that's a really nice measure to show how convergence would go. So there's different ways to compute single numbers from the whole grid. Does that answer the question?
Yes, it does. Thank you.
Okay. And yes, you can see everything that just says time series. And then available variables, what you would have, there's some 1D output just along a line. If you care for a spherical symmetric star, and this is spherically symmetric star, of course, this is all that really exists. And then 2D data in the various coordinate planes, X, Y, Y, Z, and XZ, that you could all plot, that are output by the simulation to disk. You can always choose what you want, but these are the ones that we outputted. There's no 3D output, not so much because it's not useful. In fact, 3D output is often very useful, and it might even be the best thing to output for you because it's in some sense the fastest thing to output. But this is a tutorial server with a limited amount of disk space. I don't want to dump gigabytes of data there that you can't use. All right, so let's plot this thing similar to what we had before. It's going to look visually very similar, but it's actually a different thing. So you can see how this works. So I have my sim object, that is the content of the simulation directory. Then I wanted a time series, and I wanted the maximum time series. So that's the information that was provided for me. There's a time series that computes the maximum of the variable rho. Similarly, there was a time series of the maximum of the pressure. That will also happen to be at the center of the star because that's where the highest pressure is. So I can load these two up. I can't execute them individually. And then I can set parameters for the equation of state that was used. These happen to be the same one that were in the parameter file. I just know that they are, I just hard code them. The value of K, the polytropic K that was shown by the talk on nuclear equations of state is 100. and the gamma, the adiabatic index, is 2. That's standard neutron star stuff from the, I don't know when this was first introduced. It's probably all wrong, but it's what people typically use. And that lets you code up the equation for the polytropic pressure, which was rho to the gamma with some factor in front. So what this actually does is it says, okay, I know what the pressure is from the simulation, pressure, and I'm going to additionally recompute it based on just the density. And if the equation of state that simulation simulated actually happens to be the one that I'm coding up here, then of course cold pressure and pressure should be the same thing in the end. And that's what we're actually testing here. There's a little bit of physics to it, but that's kind of what you're going to see. So, and then otherwise plotting looks pretty much like it looks like a matplotlib. You give it an X label and a Y label. Then you can plot time series data by giving it a time, an X and a Y value. So T and value, give it a label, give it a legend, and then we can plot it, and then it computes a maximum difference down here, just for kicks and giggles. Let me click enter. So it turns out what that maximum observed difference was. It's 1.952 times 10 to the minus 18, and that is basically floating point round-off numbers. Might not be quite floating point round-off because the numbers weren't quite order of unity, but for all intents and purposes, this means it's exactly cold. There was no heat or anything in there. You can also see that there is actually 2 lines, or maybe if you don't see, that tells you the same thing. These things lie on top of each other. The cold and the hot pressure, the cold and the simulation pressure are the same. And you see the figure looks pretty much the same as what I had shown you before, even though it's actually the square more or less of what you had. But to your naked eye, it looks okay. All right, let's plot the actual pseudo-color plot that we had before. This is how this is actually done. You see it's a little bit more code. This is why the script is useful, but it's also not too bad. It all has very easily understandable values. You would, again, you have the simulation directory. You have the grid functions object now, because now we're talking about grid functions, not time series anymore. You want just the XY plane of the row variable, and you want it at t equals 0, iteration number 0. That gives you back just that slice at that particular time. That gives you the raw data, which we can't plot because it uses mesh refinement, and there really isn't any easy way to plot mesh refined data. Instead of what you want to do, given that your monitor actually doesn't mesh refine anyway, you interpolate it onto some sort of uniform grid, and then you plot this one. That's what the next line here does, row XY to uniform grid data. You give it a box going from x equals 0 to x equals 10, so a square actually. Then you say, I want to have 100 data points in there, and it just interpolates it uniformly onto that data. That gives you now a 100 by 100 uniform sampled box of data that you can easily plot on your monitor. Yeah, a couple of extra options. These don't work, right? And then, oh no, it does work. And then there is trickery in there that lets you actually provide data where you don't actually have data. The simulation cheats and knows it's a circular symmetric star, so it really doesn't simulate the whole star round and out, it only simulates an octant of it, just one piece of it. And you can reconstruct what the value in the other octants is by just mirroring it as you need to go, because you know it's circular symmetric, so if it's here, it's the same value as it is over there. And that's what these 2 commands here do. They give you something that then plots the whole star. And that's not what you get. It's just as chunky, of course, as what I had shown you before, because it's the same data. But you can see it's now the whole star. While what we had shown you before, let's scroll up, you saw it's just a quarter. So the symmetry reduction just kind of takes this data you have here, this data, and then it mirrors it so that you have something that looks the same. This is purely for your visual pleasure and having a nicer plot. Of course, it's the same data all the time. All right. Any questions on this? Does this look exciting? Believe me, this is nice. You have to do this by hand. This is much more work. All right, and I think that's the end of it. There's one more magic cell at the end that really is of no use for you, but we've just made sure that there is a representation of the data that you're supposed to get in the notebook in a way that you can show it without having to run anything. And if you run the notebook on your laptop, you don't know necessarily if the answer you're going to get is correct, but we do have the correct answer shown already in here. And that's all this is. This is some extra magic. And I think that's about it. I'm 25 minutes early, but I'm not sure if you necessarily mind so much. If there's interest, I can show you a little bit how these parameter files are structured, what you can set there. But we can also have a 5 minutes break or so in case somebody. Hear me?
There's a break already after this.
Okay, good. Then I can show you quickly a little bit what the parameter files look like.
Someone raised his hand.
So, okay, then.
Roland, I have a question.
Yep.
So for the QubIT, I'm wondering if does this just automatically works with the QubIT data? Because it seems like it just takes input of row dot I guess the H5 file and just directly outputs it in the Python. So I'm just assuming, for example, if I want to plot the mesh in the this Python file, is it possible with QubIT?
I'll let Gabriela answer that. Do you have a mesh plot interface?
Yes. So QubIT reconstructs the grid from QubIT. So I wouldn't say any information, but definitely grid structure is available within QubIT. So you can plot coordinates, you can plot like the various components. For efficiency, QubIT tries to reduce all the information. So, for example, if you have a single rectangle level with multiple components, we will merge all the components in a single object, so it's much easier to deal with. So, if you want to plot the grid structure in terms of like components that is MPI ranks, essentially, you can do that with this caveat that sometimes QubIT tries to outsmart you and reduce the amount of work that it has to do. I think there's a script block that is on the website.
Okay. I'm not sure. Did this come through? I know the transcript got confused.
I can come there.
Yeah. I think I get some of these.
Okay.
And if you mind if I just go further on with another question. So with this also, I was also just quickly browsing the website, and I found that it seems like it's recently been kind of working on the gravitational waves with quasi-local measures and apparent horizon finder, and would this also work in, like, for example, volume integrals?
I think volume integrals has a very non-standard way to output stuff. So and market is very complicated. So there is some support in the sense that QubIT knows about it because it knows how to avoid it. Because otherwise it gets confused. So you have to write, if you want to use volume integrals, you have to write an answer yourself, but that shouldn't be too hard.
Okay.
It's not there, but it is.
I would say base functionality, even if you have to write your own parser, taking into the base functionality of QubIT, like the base functionality in time series, in order to like remove duplicates and things like that. Like a lot of those things can be used very easily to write your own without having to like worry about this on your own. Because I know like if you do a lot of like restarts, you have like you batch pools, do like restarts, and you have separate directory structures. You tend to always have like some overlap in the data, and the functionality of QubIT can be used very easily to make custom parsers. But even if it's volume integrals or your own custom story, it's very nice sort of work.
Yeah, some of us on that. We rely on the parser that we use to that already.
So let me just rephrase the question. I think you're really too quiet. So you're asking whether there's a specific parser being provided or how one would write one's own parser?
Yeah, because the many like we might need to have our own parser. And a couple of custom problems we have to write parser, but you can know that's what right? Yeah. So when you see, for example, sim.grid function.xy and so on, what's happening there is like QubIT knows what output to expect. So I coded up like a parser to openfy with headers and with HTML keys. So that QubIT organizes all this information so that you can access the dictionary. So what you have to do is your output is a whole time period. What I would do is you already have chains of time series organized with the output that you have. But for most of it, the assumption is that you have carpets. So what you can do is you can go into the data structure and read about the works on the time series and say, okay, if I have files that have this type of like naming convention or header files, whatever, it's up to you on how you define your file. You have to put the logic of how to define those files here. So I don't know if it makes sense. What I'm saying is that there's already discovery processing, but you have to start with it. How to understand what variable kind of file and what type of object to expect on the file. So, but this is not something, it's not like a plugin, you have to go and change the code.
Okay. So basically doable, but you have to modify the code. And you should try and use the existing parsers as a starting point.
Yeah, so I can say words on why multimedia process is important. And the reason is that it's very difficult to make a sensible organization for multimedia blocks because you have maybe something that the integration is from 0 to 100, and it's from outside of 25, and it's within 50. So there's all the different options. So I found difficult to find something that makes sense. They're organized all these different options with the volume interval. And then the steps to implement this will be to read the header file, which are the first lines, which I think they are commented out with R symbol. Write a regular expression that extract from there the type of variable that is inside and present this as a dictionary and ultimately as a actually it's definitely doable, but I think it has to be done in such a way that it makes sense.
It's exactly what I read. If he's talking about the ones from WBU, exactly what that's be.
Okay.
Those are the WBU thorns.
Yes.
Yeah. I think that's exactly what would have to be done. Parts, the comments that would contain information about the rows and then present them useful.
Okay. Right. Thank you. I hope this was all understandable to those remote. Not sure how good the microphone is, but no complaints have been raised so far, so it's probably okay. Okay. Any more questions? Any more things that you would like to know, comment, or anything else? Yes, please. Have we integrated with ParaView? VTK, but not ParaView, I think, right?
If ParaView supports uniform data, you can use QubIT to have like an outlier rate. ParaView is quite abundant. You can use ParaView. I don't know how to use this.
But Cactus has
There is so not for QubIT, and actually before QubIT, there is a plugin that directly reads the carpet file format, the 3D, 2D files into Visit, not ParaView, Visit. And that was traditionally used to make these plots. In fact, most of the ones that I showed you when I said, oh, this is what you can do, all the 3D ones were effectively done with Visit. So same underlying infrastructure, of course, both use VTK, but different GUI, different approach to the GUI. It's still part of Visit. You don't have to download anything. We have newer versions of the Visit reader that is a little bit better in some sense, but hasn't really made it upstream yet. So, yeah.
But is there any look into comparison or no?
You could, it's just nobody has ever done it because the people just used Visit, and then there was Visit, and people normally say, it doesn't really matter which one. But if you want to do ParaView, given that there is a Visit reader, porting that Visit reader over to ParaView is probably fairly trivial as long as you get hold of somebody who knows how ParaView works, and ideally a Visit developer as well.
Yeah, we were trying to install Visit on a cluster recently, but I mean, Visit has, if you can't use the precompiled version, then you have to deal with their custom modified libraries that get transported with it, and
But you,
obviously it would be nice to move away from that.
yes, I don't think that ParaView would be much easier, though, admittedly.
I think you can install it.
Well, yeah. But I think that the tricky piece of this is you need a mangled version of Mesa, for example, and the VTK gives you trouble. And since both ParaView and Visit use VTK, You probably switch one sort of pane for the other, but yeah, if you had ParaView, but now there is currently no direct ParaView support, other than I believe that for a while ParaView had a visit converter plugin or so. That still works. You might be able to use the visit plugin, but it's not my thing. I will take no responsibility for it, not to suddenly delete your home directory.
Roland, may I make a comment? This is Eric.
Yes.
Okay, so QubIT uses its own file format, and if you want to read it and to visit a ParaView, you need to write a reader for that. In the future, we are probably going to move to a standard format, and one of these standard formats is OpenPMD. And I think there is a reader for OpenPMD for ParaView over Visit, or someone is working on it. Or anyway, if you were to write a reader, you should probably write a reader for this standard format, OpenPMD. And then not just Cactus, but other toolkits could also write files that can be visualized with ParaView or Visit.
Yes. And if you want a hackathon project, but that would be really complicated, you could write an OpenPMD writer from QubIT, but that's not going to finish in a day. But it's not that much longer, a week or so. Anyway, any other comments, questions? Okay. Then let me try and see if I can show you a little bit how these parameter files are structured. And those of you who use Cactus, please stop me if I say something that's utterly wrong, because I might not necessarily notice. Okay, so let me go and just go through it. So this is our example, very simple, single spherically symmetric star evolution file. Sometimes it's prototypical for others that you might also have, at least if you have fluids in there. If you have something else that you want to simulate, it's highly recommended that you start from a gallery example. We have gallery examples for binary neutron star, binary black holes. This thing is in there somewhere. There is scalar waves on a curve background, I think. So I would start from those. Nobody ever really starts with a parameter file from scratch. Certainly not I, ever, because they're somewhat complicated. But if you have one that works, it's easy to change it slowly so that you go to what you want. So start from a big one that already works, that's roughly what you want, and go and modify it. If you find nothing, you can send an email to the mailing list, and very often people will be willing to share parameter files that they have used. Sometimes they might not work because they might rely on private thorns, but you get the general structure. All right, so let me give you kind of a basic overview. So as I said, it's mostly just name-value pairs. The first block of values that you will see here are called active thorns. They actually tell Cactus when it runs, what modules do you actually want to use. You could compile in more than what you want, and then select which one you want at runtime. Some of them have very obvious names. There is a module called time that literally just keeps track of your simulation time, and also is a convenient way to specify, say, a kernel condition. There's the MOL thorn, method of lines, that's responsible for time stepping. So that's one of these infrastructure thorns that we're providing for you that you normally don't have to write yourself. So these you will very often find. There's a lot of base thorns, like these, that other things are built on that let you specify things. Mostly you just copy them from where they were. You copy these activation lines and then you're good. And then you set options for them later on. Sometimes you might find that people put the actual physics thorns at the end, or maybe it's sorted alphabetically. It really doesn't matter. You could have one active thorns line with all the ones in there. You could have one individually. You can spread these active thorns lines throughout the parameter file, pretty much whatever you do, as long as you know what you're doing and you can still read what you have done after a year. But these just activate modules. Then once you have them activate, you can give different options to the different modules. And I'll skip kind of the boring ones for now, and I'll maybe go to the ones that I think are more likely that you actually want to change. So one block that's probably of interest for most persons is how do you actually specify the grid that you want your simulation to live in? So this is done by a combination of the carpet thorn, which is the driver thorn that kind of needs to know everything. Then the card grid 3D thorn, which gives you coordinates, Cartesian coordinates in 3D, given a name. And the cohort-based thorn, which is this base thorn that just lets you describe what does the grid look like to everybody else. And these three work together to give you coordinates and a grid. Now, If you look at the coord-based one, here it has 6 options that specify to you kind of the shape of the cube. That's the arena in which your simulation will run. And that's true for this particular type of simulation. There's other types with curvilinear coordinates where it's a bit more complicated. But for Cartesian coordinates, Cartesian single block ones, this is what it looks like. And it kind of has obvious names. You give an x-min, y-min, z-min, which is the left edge here. This is all 0. And then you give a max value, which is the upper edge, 24 here. So if my star was 10 in size, this isn't really much bigger than my star. This is why the simulation just barely survives. If you run it long enough, then eventually it dies because it's too small. So this also tells you you're only doing a single octant from 0 to 24. There's nothing in the negative areas ever, which is cheaper, of course, because you only simulate an eighth of the full simulation. If you now have a bigger one, you would change this. You also see that this is only kind of the overall arena where your simulation is. It doesn't have anything in there about mesh refinement. Certainly this wouldn't work. I need to have a bit more resolution around my star. That's defined somewhere else. This really just says this is the arena where my thing should evolve in. So I now have the size of the box that my simulation wants to live in. I have to give it some sort of resolution. The coarsest one actually that we'll have in my system here, I just give the x, the y, the z values, which is the grid spacing that covers that initial box. 2 in size. So that means I have 12 points that cover my whole simulation, which is why you saw these chunky little pixels, because it's just that coarse. And if you wanted to make this into something that's saner, you would increase or would decrease these values for higher resolution. You would want to make the grid bigger. And then there's kind of ones that you pretty much always have to set. This avoid origin equals no, take it as a standard value. Historically, it used to have a different value. Historical values never change, so you always have to set it to no now, even if this is what everybody uses. The domain equals full is similarly something that's a little bit historical. It essentially tells coord-base to treat this as the full domain, not to think there's any implicit reflection symmetries in there. There is, but coord-base doesn't know about. And CurtGrid 3D type coord-base just means get all the information you need to know to construct my coordinates from coord-base. Don't try to make it up yourself, which is the alternative, historically used way of doing things. And then the same thing for CarpIT. CarpIT could be told explicitly what the grid looks like. Then you have to tell CarpIT and coord-base and probably your evolution points. And almost certainly these 3 will not agree, and then everything breaks down. So there's options to tell it, don't do it yourself, query coord-base. These are the standard ones you want. When you look at a parameter file that doesn't have these, be worried that it might be a parameter file that's older than you are. And then the next block that's actually of interest is now for CarpIT Regrid 2. That actually gives you mesh refinement. CarpIT Regrid 2 is the module that describes to CarpIT a way of refining your mesh. It is designed around the idea of having nested boxes, which was what people traditionally used with Cactus and CarpIT. So if you have, say, a black hole, you would put a box around each black hole and move that box as the black hole moves. If you have a neutron star, you put the boxes around the neutron star and you move them as the neutron star moves. This works great for these complex objects, for these compact objects, because you know where they are basically, either because the density is measurable, or you know where the center of the black hole is. And that makes for a very cheap way of describing where do you want the resolution. Nothing can go wrong. It fails, of course, if you have something like a tidal tail. If you pull material out of a star, and this now forms a banana-shaped string of material that flows away from the star, that doesn't really look like a box. For this, you want a different type of mesh refinement based on features, which isn't describable with CarpIT Regrid 2, and isn't traditionally used with CarpIT either. Can do it, but it's not normally done. So CarpIT Regrid 2 deals with boxes, and the boxes are called, each box has a center that describes, well, where is its center and where does it move to? Here, since I have a single star, I only say one center. So num centers is set to one center centered on the star. Then for each of the centers that I have, each of the boxes, I have to tell how many levels of mesh refinement could I possibly ever want there. Or in this case, actually, do I want there? In this case, I want 2, and the _1 here means for the first center. So the parameter file syntax is intentionally very simple. There's no nesting, there's no curly braces that let you mess things up in any way. It's really just name equals value. At most, it's going to give you 1D arrays with brackets. And that means that usually when you have multiple things that are the same, so for example, I have 10 centers, then usually name the first center center underscore 1, second one is center underscore 2, center underscore 3, and so on and so forth. So that makes for simpler parameter files. And usually we found it's worth the loss of flexibility to have more easily understand parameter files. If you wanted to, you could have parameter files that have lots of nested things, but then your source code, this thing will look like source code and will look like a C file, which probably is harder to read and harder to parse. Anyway, so 2 levels for our first center. We already have 1 level, the coarsest one, it always exists. So essentially means give me 1 extra level. And that extra level is specified in the next line. We give the radius, or the radii actually, for my first center. So radius underscore 1 means the first center. Then it's an array which tells for each refinement level what's the radius of the box on that particular level. Here I only have 1. So bracket 1 is the first refined level. I want a radius of 12. The whole grid was 24. This has a radius of 12, so it's half the size. And given that the star has itself a radius of 8 to 10 or so, it's reasonably close to the surface of the star. So this now prescribes you a star. If you wanted to have more levels, then you would add extra levels here, maybe set this to 3. Then you could add extra ones down here. Let's see if I can do this. Oops. Let me see. Yeah. Wow. Let's be careful. Okay, so if I want an extra level, now the first refined level was level 1. The next refined level is then level 2. Oops. So I put in a 2. And then I want the radius, presumably it should be smaller so that they're actually properly nested. Otherwise, QubIT either complains or silently makes the outer one big enough that it contains it. Depends a bit on how it's configured. So usually we go factors of 2. So now I would have a size of radius 6 in there. And if you now had a black hole, you would add more and more because a black hole itself has a size of say 1-ish or so in natural units. So that's how you add these. Yep. Where do you want 34? No. No, they need to be contained. The final levels need to be contained in the coarse shell levels. So if you wanted something where you have a coarse region in the middle, surrounded by a fine region, you would have to put slabs of fine refinement level around it. You have to build that particular geometry by hand, which would be somewhat difficult to do. You could do it, but it really isn't designed. You'd have to build it up out of Lego blocks, basically, pizza boxes in some way or the other. It's doable, but nobody has really ever had to do that. But yeah, if you do a disk simulation, accretion disk, you might want to do this where you have low resolution in the center. In particular, if you do Cowling approximation where the space-time is given, then you have low resolution in the center. You kind of put a pizza box shape, high resolution for the disk around it, and then coarse resolution again. Doable, but hasn't really been done very often. So it's not terribly well suited. You could easily add it, but it's not good. 2 minutes. Okay. I'm told I've used up all of my time. So
deciding whether you're subcycling or not, is that always inherently?
Let me see if that's specified here. So QubIT technically always subcycles. So in the sense that subcycling means that the different refinement levels step separately from each other. And if normally you would have to step the coarsest level first so that you have data that you can use to interpolate into the boundaries of the fine data when the fine level starts. Technically, QubIT will always do that. You can set the time stepping ratio between the different levels to 1, which means they now all exist on the same time all the time. That's one thing that you might want to do. That means you can get away with not having any buffer zones. It will still step them independently. QubIT X, on the other hand, recognizes this and will put everything that steps with the same frequency into a box and step them all at the same time. Therefore, you get better efficiency. And there is a parameter called time refinement levels, or time refinement factors, which probably isn't in here, but is in the binary black hole example that you can set to give these factors. It's always factors with respect to the finest level. So the parameter files start from the coarsest level. QubIT has to start from the finest level, just because of how the math works. So you have to be a bit careful. But yeah, you can, but you're not going to get exactly say what paraf you would be doing if you do all refinement factors to 1. Right. Okay, Eric is not shouting at me. I must not have said something that's too wrong. Okay. Any other questions? Otherwise, I think with 2 minutes to spare, I'll not incur the wrath of the organizers and stuff. Right. Thank you.